Dear students, welcome to a class of topology. Today we are going to discuss about the property of metrizability in topological space. A topological space X2 is said to be metrizable if the metric of X if the topology of X, that is tau, is derived from a metric. When the topology is derived or induced from a metric, that kind of topologies are called a metrizable topology and the space is called a metrizable space. For example, discrete topological space is a metrizable space, or the discrete topology is a metrizable topology. Metrizable space. That means the discrete topology is metrizable. However, how will you prove that the topology is metrizable? So it should be came from a metric. So I can say that the discrete topology is actually induced from the metric discrete metric. What is a discrete metric? Consider discrete metric on X, that is D from X cross X to real line, such that D of xy is defined as piecewise defined function 0 when x equal to y, if x equal to y, and 1 if x not equal to y. This metric is called a discrete metric. Okay, and we know that every metric space is a topological space. So by considering the metric space X with this metric, discrete metric D, XD is a discrete metric space. Then XD is a discrete metric space. And we know that every metric space is a topological space, correct? Since every metric space is a topological space, and what is the topology in that metric space? The topology in the metric space is defined by taking all the open sets in the metric space, correct? With the topology tau is defined as collection of all A subset of X such that A is open in the metric space XD. When you say that a set is open in a metric space XD, that is tau equal to collection of all A subset of X such that every element of A is an interior point of A. And what is an interior point? Interior points are the points such that if A is a subset of a metric space XD, and we say that a point small x is an interior point of A, corresponding to every point there should exist one neighborhood which is fully contained in A. Correct? There should exist some neighborhood which is there should exist some open ball which is fully contained in A itself. So for every small a in capital A, there should exist an open ball. Therefore, there exists a radius. There exists some radius are greater than 0 such that real number are greater than 0 such that some open ball is the representation BD of A comma R. This is the representation of open ball centered at A with the radius R with respect to the metric D. Okay. The open ball BD of AR is contained in A itself. Then we can say that A is open in the metric space XD. Okay. Now what are the subsets in this metric space which satisfies this condition? We know that in a discrete metric space, every subset is an open set, correct? So this collection will contains all the subsets of capital X because the metric is a discrete metric. Then this collection consists of A subset of X, where A is any subset of capital X. When a topology contains all the subsets of capital X, Then what will be that topology? This topology is nothing but the discrete topology denoted by 2D, discrete topology. So you can say that when a set have a discrete metric, that metric can induce a topology, and that topology is nothing but the discrete topology itself. So that discrete topology is a topology induced from discrete metric, and this topology is called metrizable topology. So which is an example for metrizable topology. So which implies discrete topology 2D is induced from discrete metric. Discrete metric, therefore it is metrizable topology. Metrizable topology, it is a metrizable topology. Now another example for metrizable topology. Another example is, you consider real line with the topology of real line, that is usual topology of real line. What is TOU? Usual topology is defined as set of all A subset of R such that for every A in A there exists some real number R greater than 0 such that interval of the form A minus R, A plus R is fully contained in A itself, entirely contained in A. The standard or usual topology of real line. This topology is also metrizable, and this topology is derived from or induced from usual metric of real line. What is usual metric? The usual metric on R is D from R cross R to R such that it is defined as, what is D of xy? Usual metric is modulus of x minus y. Correct? Then we can consider the metric space real line with this metric D. It is a metric space. And when you have a metric space, we can induce a topology from the metric and consider the corresponding metric topology. Consider the corresponding metric topology tau. What is this tau? This consists of set of all A subset of real line such that A is open with respect to the metric real line with the metric D, the usual metric, which is equal to collection of all A subset of R such that, what are the open sets in the real line with the usual metric? For every A in A there exists, that means every point of A should be an interior point. That means for every A in A there exists some radius such that interval, the open ball in usual metric is of the form open interval A minus R, A plus R. So for every A in A, interval of the form A minus R, A plus R is contained in A for some R greater than 0 in real number. So this is the definition of open set in usual metrics of real line. So which is nothing but, which is actually same as the definition of usual topology. Correct? Therefore, these subsets are actually formed from the metric D, which is coincide with the subsets in the usual topology. So which is nothing but TOU itself. So the usual topology is induced from usual metric on real line is a fact. So which implies TOU is a topology derived from usual metric of real line. Therefore, it is a metrizable topology. So what is a metrizable topology? When the topology is derived from a metric. And discrete topology and usual topology of real lines are metrizable examples for metrizable topology. So corresponding to every metric space, there is a topology which is induced from the metric. And also note that every topology need not be a metrizable topology. One example for a non-metrizable topology is indiscrete topology. Every topology there exists topology. There exists topology which is not derived from, which is not metrizable. Example for a topology which is not metrizable. Example is indiscrete topological space. Indiscrete topological space. What is indiscrete topology? When you consider a non-empty set X together with the topology, I denote tau I, where tau I consists of only two elements, empty set and full set. Okay, we can prove that this topology is not a metrizable topology. For that, assume this topology is derived from a. Now to prove this, it is not metrizable. Suppose that this is a metrizable topology. Assume indiscrete topology tau I is metrizable. Metrizable topology. Then it should be derived from a metric. Then there exists a metric. There exists a metric D such that tau I will be is induced from the metric D. Okay. Therefore, we can consider the metric space. The metric space X with D. Then what will be the open sets in the metric space? When the topology is derived from D, the open sets with respect to D is also same as the open sets in the topological space. Here the only open sets are empty set and full set. Therefore, the only open sets in this metric space are also empty set and full set. Then the only open sets in the metric space XD are empty set and X itself. Now, when a space is metric, satisfies the properties of a metric space, then it also satisfies one important property of metric space, that is Hausdorff property. Hausdorff property or T2 axiom. This is also called the T2 axiom. Okay, and this property says that if x comma y are two points in the topological space X tau such that x not equal to y, then this property says that there exist disjoint open sets U and V such that x belongs to U and y belongs to V. That means when a topological space has a Hausdorff property, then if you take any two distinct points in that space, then there will exist open sets U and V disjointly to cover x and y. That means distinct points can be separated by disjoint open sets. That is the meaning. And every metric space has this property. Okay. Note that every metric space has Hausdorff property. So, our metric space derived from, or metric space XD also has this Hausdorff property. Correct? Thus, our metric space MS is metric space, XD also has Hausdorff property. Okay. So let x comma y be any two points in capital X such that x not equal to y. Then there should exist open sets, disjoint open sets, that is the important one, disjoint open sets U and V such that x belongs to U and y belongs to V. and these open sets are belongs to capital XD, correct? But the only open sets in capital XDs are empty set and full set. We want two open sets U and V such that X in U and Y in V, and U and V should be disjoint also. So we can consider only one open set from this metric space to contain elements, and we can't find out two disjoint open sets simultaneously, so that this metric space fails to have this property. But there exists only one open set, actually only one non-empty open set. Therefore this metric space XD fails to satisfy this property. That which is a contradiction. Every metric space satisfies this property. So which is a contradiction? Therefore, we cannot develop a metric like this. That means our topology is not a metrizable topology. Therefore, tau I is not a metrizable topology. Okay. Now, we are going to prove that this property of metrizability of topological space is a hereditary property. What is a hereditary property? When X tau is a topological space, has a property, then every subspace of X also has the required property. Okay, so we are going to prove that metrizability is a hereditary property. Theorem: metrizability is a hereditary property. So how will you prove a property is hereditary? Let us assume that suppose a topological space has a property of metrizability. Let X tau be a topological space such that tau is metrizable. Tau is a metrizable topology. When tau is a metrizable topology, there is a metric such that tau will be induced from that metric. Then tau is induced from a metric D on X. Okay, we have to prove that this property is hereditary. That means we want to prove that every subspace of X tau has this property. So I am considering a subspace of X. Let Y be a subset of X. Okay. Then we have to prove that the subspace, topological subspace. What is a topological subspace? Y with the topology. What is the topology on subspace? That is tau restricted to Y. Y tau restricted to Y is a metrizable space. We have to prove that the topological subspace is also metrizable space. That means the topology on Y. What is the topology on Y? Tau restricted to Y is also induced from a metric. This is what we want to prove. We already have a metric D on X. In order to prove tau restricted to Y is induced from a metric, we want a metric on Y, and the corresponding topology developed from that metric is actually equivalent to tau restricted to Y. This is what we are looking for. But we already have a metric D on X. Consider the metric space XD. Consider the metric space XD. Okay. Then when XD is a metric space, every subset of a metric space is again a metric space, and that is called a subspace. And the metric on the subset is nothing but the restricted metric on X. when you have a metric space XD, then every subset of X can be considered as a metric space, and the metric on the subset will be D restricted to Y. That means the function is restricted to the subset. Correct? Then Y with D restricted to Y is a subspace of XD. Is a subspace of XD. So, using the metric of X, we get a metric on Y. Now, YD restricted to Y is a metric space, so that we can find out a metric topology on Y by taking open sets from D restricted to Y. Correct? Then the metric space, MS denote metric space, YD restricted to Y is a topological space with the metric topological space with the metric topology. What is a metric topology? Induced from D restricted to Y. I denote it by some U. Denote it by U. And what is U? U is the metric topology on Y induced from the metric D restricted to Y. Then what will be members of U? What is U? Set of all A subset of Y. Correct? Because U is a topology on Y, therefore U contains subsets of Y, not subsets of X. Okay, not all subsets of X. We are considering only subsets of Y. So A subset of Y such that, because it is came from the metric D restricted to Y, A is open in the metric space. Y D restricted to Y. Okay. Now we have to actually prove that the restricted topology tau restricted to Y, which is also a topology on Y, this topology is metrizable. That means we have to get a metric on Y such that tau restricted to Y is derived from the metric on Y. Now we have a metric D restricted to Y on Y, and the topology derived from D restricted to Y is denoted by U. Now we are going to prove that tau restricted to Y is equal to U, or equivalent to the topology U. If I prove this, then since U is derived from the metric D restricted to Y, tau restricted to Y is also derived from the metric D restricted to Y. Using the statement, we can say tau restricted to Y is metrizable. So the next claim is tau restricted to Y is equivalent to U. Okay. Now, before proving this claim, when you say that a set is open in a metric space XD, this is an extra fact you have to remember. A subset of a metric space XD is said to be open if every point of A is an interior point of A. Interior point of A. That is, for every A in A, there should exist an open ball. Open ball is actually denoted by BD of AR, open ball with the center A and radius R, which consists of elements some B in the space capital X such that the distance between the D of A comma B is less than R. These are the elements, which are the elements B in script X such that D of AB is less than R. And this is called open ball centered at A with radius R. Okay, when a point is an interior point, if there exists an open ball BDAR such that this open ball fully contained in A, that is the meaning of a point is interior point. Every point of A is an interior point of A. That is for every A in A, there exists some r greater than 0 such that the open ball centered at A, radius r is fully contained in A itself. This is the meaning of a point is an interior point and the set is open. Okay, this is true for a metric space XD. When Y is a subset of the metric space XD, then Y D restricted to Y is a metric space. When will you say that a subset which is open in this subspace of the metric space? So, some capital B subset of Y is open in the metric space Y D restricted to Y means for every B in B, there exists some r greater than 0 such that the open ball centered at B, R with the metric D restricted to Y which is fully contained in B. And what is the meaning of D restricted to Y, the metric D restricted to Y? This open ball is actually nothing but BD of BR intersection with Y which is contained in B. This is the meaning of B D restricted to Y. Actually, suppose this is our metric space XT. Okay, for any point A in X, we can consider an open ball which is fully contained in A itself, means this is a kind of interval of kind of open ball in the metric space XT. When you want to restrict this neighborhood, when you want to consider this neighborhood with respect to the metric D restricted to Y, where Y is a subset of X, we are actually restricting the points of this open ball into Y. So suppose Y is a subset of X and A is a point here. This is our open ball centered with A and radius R. Then this open ball may or may not contains elements of Y and elements of Y. Then if you want to construct B D restricted to Y AR, we are just considering the points of this neighborhood of this open ball with points in Y. So this is nothing but intersection of the open ball with set Y. So I can write B D restricted to Y BR is contained in B means B D of BR intersection Y is contained in B. Okay, you have to remember all this representation to prove this theorem. Now back to the proof. Our claim was tau restricted to Y is equivalent to the topology U. So we are taking arbitrary one element from tau restricted to Y and we are going to prove that that is also belongs to U and the reverse part. So let us assume some V be an element in script U. Okay. Then what it means? What are the elements in U? Script U is a topology formed from the metric D restricted to Y. So which implies V is open in the metric space Y D restricted to Y. So which implies when a set is open in the metric space Y D restricted to Y means there exists or for every small v in capital V, there exists some RV greater than 0. Corresponding to every point, the radius will vary. RV greater than 0 such that open ball B D restricted to Y V, RV is completely contained in V itself. Okay, what you want to prove? We want to prove our set capital V belongs to tau restricted to Y. And what is tau restricted to Y? Tau restricted to Y is what is tau restricted to Y? Tau restricted to Y is set of all A subset of Y such that, or set of all A intersection Y, I can write it as set of all A intersection Y such that A varying over members in tau. This was the definition of a subspace topology. A intersection Y where A is a member in tau. Okay. Now to prove V is a member in tau restricted to Y, we actually want V can be written as some A intersection Y where A is a member in tau. Okay. Okay. Now this is contained in V implies by the representation BD of VRV intersection with Y is contained in V. Now you consider collection these kinds of neighborhoods or these kinds of open balls. What is this actually? We actually considered for every what was V is an element in U. What is U? U is a topology on Y, so that V is nothing but a subset of Y. Okay, so V is a subset of Y, and we take a point for every V in V there is a neighborhood which is fully contained in V itself. Okay, now we are collecting these open balls with respect to the metric D. Okay, consider these open balls, open BD of VRV, their union varying over V in V. We are collecting all these neighborhoods of elements in V with the metric D of X. Okay, and I call or I represent this union as a set A. Let A equal to union V varying over V BD of small v comma the radius with respect to V. Okay, then what is this? This is an open ball, and these open balls are belongs to our metric space XD. We know that in a metric space every open ball is an open set, correct? In an open set, in a metric space, every open ball is open set, and in a metric space arbitrary union of open set is open. Here every BD of VRV is an open set, and union of such open balls, such open sets is again open in a metric space, and arbitrary union of open set is open in a metric space. Therefore A equal to union V in V BD of V comma RV is open in the metric space. Which metric space? In the metric space XD. In the metric space XD. And what is the metric space XD? XD is a metric space which is actually defined from the topology tau, which was metrizable. When the topology tau on X was metrizable, we developed a metric D. So when a set is open in the corresponding metric space XD, that set automatically belongs to the metrizable topology from D. Therefore, A is an element in tau. Why? Since tau is induced from D, the metric D. Okay. So A is a member in tau. Now you consider what will be A intersection Y. A intersection Y. What is A? Union V in V BD of V comma RV intersection with Y. This is nothing but union of V in V BD of V comma RV intersection Y. This can be written union V in V. What is BD of V comma RV intersection Y? This can be represented as BD restricted to Y of V comma RV. Okay. And what is this? This union of these sets are nothing but our capital V. Corresponding to every small v in capital we are considering open balls in V itself. So their union is nothing but V. So what is A intersection Y? A intersection Y equal to V. What is V? what is A? A is a member in tau. So which implies V can be written as A intersection Y, where A is a member in tau. When V can be written like this, V will be a member in tau restricted to Y. So when you consider an element V in U, if V in U, then V belongs to tau restricted to Y. So U is a topology weaker than tau restricted to Y, which is equation number 1, inequality. Now to prove the reverse implication, let us consider an element some A in tau restricted to Y. Okay, I change the letter A to, suppose let V belongs to tau restricted to Y. Then every member of tau restricted to Y is of the form Y intersection A, where A is a member in tau. Okay, we want V is an element in U. That's for that we have to prove that V is a set which is open in the metric space Y D restricted to Y. Okay, for that we have to prove that V is contains all points which are integer points. So we are arbitrarily taking one element from V. Let small a is an element in V. Then A is an element in Y intersection capital A. So which implies A belongs to Y and A belongs to capital A. And what is capital A? Since capital A is member in tau implies tau is a topology which was metrizable. When it was metrizable, its elements are the open sets in the corresponding metric space XD. Therefore, A is open in the metric space XD. When a metric space set is open implies for every A in A, there exists R greater than 0 such that the open ball BD of AR will be completely contained in A itself. Correct? So this will be true for every element in capital A. So now we have A is an element in capital A. So corresponding to this A, there will exist some radius with this property. Okay. So which implies our A is an element in Y and A is an element in BD of AR which is contained in A itself. So which implies A is an element belongs to BD of AR intersection Y and which is contained in BD of AR is contained in A. So A intersection Y. And what is A intersection Y? Which is called as our set V. So when you take an element small a in V, then we have a radius R greater than 0 such that BD of AR intersection Y will be fully contained in V itself. So which implies for every V in V, there exists R greater than 0 such that what is this set? BD of AR intersection Y. BD of AR intersection Y is A belongs to BD restricted to Y of AR which is contained in A intersection Y, that is equal to V. So which implies for every A in V, there exists R greater than 0 such that A belongs to BD restricted to Y of AR contained in V itself, which implies every point of V is an interior point of V in the metric space with respect to the metric D restricted to Y. So which implies V is open in the metric space Y with the D restricted to Y. So when which is a set which is open with respect to the metric D restricted to Y, that will be belongs to the topology induced from D restricted to Y. And what is the topology induced from D restricted to Y? That was U. So V belongs to U. When you take an element V in tau restricted to Y, that is again belongs to U, which implies tau restricted to U is contained in U, which implies from 1 and 2 we can say tau restricted to Y is same as the topology U. Since U is derived from a metric, tau restricted to Y is also induced from the metric D restricted to Y. So which implies tau restricted to Y is also metrizable topology. Since every subspace, since Y, the subspace Y was arbitrary, which implies every subspace of X tau is metrizable space, which implies metrizability is a hereditary property.